Welcome, everyone. In this section, I'm going to introduce GeneSys Performance Profiling Infrastructure and how it can help developers to gain insight with or without hardware implementation. My name is Hanyang Xu. I'm a third-year PhD student at UCSD Ag Lab. I'm one of the main contributors to the design, simulation, implementation, and verification of the GeneSys framework. The GeneSys Performance Profiling infrastructure consists of an accurate hardware performance counter modules in controllers, systolic array, SIMD vector engine, and memory interfaces that can be synthesized and record real-time performance in the actual hardware. And it also consists of a fast software simulator for quick compilation optimization inside without any hardware implementation. The color box highlights the hardware and software simulator in respect to the entire GeneSys framework. Note that to ensure consistency and simplicity, both the hardware performance counter and the software simulator are based on the actual instruction produced by the compiler, ready to be run on the actual hardware. As this figure shown, we place performance counters inside GeneSys controller, systolic array, vector engine, and all memory interface. The recorded statistic is passed back to host through instruction memory interface once the execution is complete. The output are text-based performance numbers or plots using GeneSys Python API. The GeneSys software simulator is a cycle-accurate Python-based simulator that simulates the execution of GeneSys architecture, including the software pipelining between systolic array and vector engine. It also integrates cacti for energy modeling. The GeneSys software simulator takes in the compiler-generated instructions and a hardware configuration file as input, and outputs the performance and energy statistic in CSV file or in automatic generated figures. The hardware configuration file includes information such as frequency, memory bandwidth, memory latency, and memory energy. Here's an example of simulator output. It contains the information about the layer, which is highlighted in orange box, compiler tiling, which is highlighted in blue box, and hardware information, which is highlighted in the green box. As the blue box highlighted here, the simulator result contains overall performance stats, include total cycle and cycle per tile, and systolic cycle and SIMD cycle separately. For example, layer 1 ReLU 2 layer is a SIMD layer, thus the systolic total cycle is 0. The performance is also broken down into compute cycle, memory load cycle, and memory store cycle, as green box highlighted. Finally, the simulator counts the number of read and write to buffers, as green box highlighted, and use that information to calculate the read and write energy, as the blue box highlights. We verify the software simulator against real hardware run, and the error margin is less than 15%. The main source of the error is from memory cycle, which is more difficult to model. Next, we showcase two simple profiling we performed to showcase how to use GeneSys software simulator for quick design insights without hardware implementation. The first profiling we did is a sweep of systolic array size and its performance gain running a matrix multiplication kernel to showcase how hardware configurations affect the performance. The x-annex of the figure is the systolic array size, and the y-annex is the normalized performance speedup running a matrix multiplication kernel. As we can see, before 60 by 64 by 64 systolic array, the performance scales with the increase of PE units, but the performance gain for 128 by 128 systolic array broke the scaling. The next graph here shows the reason for the scale of the scaling. The figure shows the runtime breakdown between compute and memory for all systolic size running that matrix multiplication kernel. The x-annex of the figure is the systolic array size, and the y-annex is the percentage of compute versus percentage of memory in the runtime. As we can see in 128 by 128 configuration, memory runtime is about 40% of the overall runtime, which explains the breakage of the performance scaling we see previously. The next profiling we did is a sweep of compiler tiling and its performance variation running a matrix multiplication kernel to showcase how compiler optimization affect the performance. The x-annex of the figure is the tiling configuration, and the y-annex is the normalized performance slowdown running a matrix multiplication kernel. As we can see, the general trend is the performance degrades as the tiling increases. This graph shows the reason for this trend. This figure shows the runtime breakdown between compute and memory for all tiling configuration. The x-annex of the figure is the systolic array size, and the y-annex is the percentage of compute versus memory during runtime. As we can see that poor performing tiling usually has higher memory runtime, which showcase how DN workloads are often memory bound. In this section, we introduce GeneSys simulation infrastructure. We showcase how this infrastructure can unveil architectural and optimization insights. We hope the work we present here can facilitate your research in a meaningful way. The main contributor to this part of the work are Dr. Sarush Gohadradi, Rohan Mahapatra, Hanyang Xu, and Lavanya Karthikeyan. Thank you for attending.